But before that, we were discussing hardening and softening, right? And so when there is cyclic loading on the material, then dislocations will start moving. Okay, and there will be slip band formation. And those slip band formations will have some speciality with them. And when you polish the surface, some of them will go away, some of them will disappear, some of them will persist. So this is why they're called persistent slip bands, PSBs. Okay. And so in this picture you see single primary slip system, and then you have slipping happening in different grains, not in all the grains. Okay. So here and there in few grains these things are visible. Okay. So these are persistent slip bands, and we will discuss this later, inclusion and extrusion, the process of, but I just wanted to show this picture to you. So you see initially you have, so this is in the first cycle, you have dislocation arrangement, and then they have started moving, and then after many cycles we see that they have arranged themselves in cell structure, what is known as cell structure. Okay, so they are moving and they are arranging themselves in a particular fashion, and this is dictated by the amount of cross slip which can happen in the material. Okay, and this ability to cross slip is dependent on many parameters. One of them is stacking fault energy. So stacking fault energy will decide if the cross slip is easy or not. If the stacking fault energy is higher, then easily cross slip can happen, and if it is lower, it cannot happen. But there are certain alloying elements which can help with stacking fault. So for example, nitrogen in stainless steel can affect this ability of cross slipping, and there has been some study which says that this is not because they change anything in the stacking fault energy, but they interact with the dislocations, and that's how they resist the cross slip. And if you resist the cross slip, then so you see again two partials, and between two partials you have stacking fault here. So this is one partial, this is another partial. And if you have cross slip and if you don't have cross slip, then there will be two different features of slip bands which will be formed, and those features are this. So in the first case you see that cross slip is easier, okay, and because of that you have planar slip band formation in this form, okay. And in another case, so dislocations are getting piled up at some barrier, and then they are cross slipping to different planes and crossing that obstacle, okay. And because of some reason, if they cross slip in a different way, then you will have a wavy form of slip band. So this will happen when stacking fault energy is not good enough. Okay, so that was the part of stacking fault energy, and then we will discuss about what happens to stress strain behavior when we do cyclic loading. But in this picture you see the effect of wavy slip and planar slip on the stress strain diagram. Okay, so for cyclic annealed condition, you see this is the curve when the material predominantly has wavy slip, and when you have for the same behavior. If you have planar slip, then stress and strain behavior is different. Okay. So planar slip is when you have easy cross slip happening. So in that case, not much of hardening is there. So that curve is a little lower than the curve which you have when you have wavy slips. So how do we get this curve? How do we get the stress strain curve for cyclic loading? For cyclic loading, how do we get stress strain curve? So what we do is you take a sample, okay, and then you can load the sample in different ways. So fatigue can be of different way. Industrial fatigue is rotation bending fatigue. So Murray's test apparatus is used. You can also have tension fatigue. You can have tension compression fatigue. Okay. You can have torsion fatigue also. So one of the tests which we have not discussed, and that is also not the part of this syllabus. So apart from tension test, compression test, bending test, there is another not that famous test is torsion test. And a lot of work on high temperature torsion, not cyclic, but also cyclic, is being done in some institute. And this machine is not very famous, but it is giving a lot of good results. So not good meaning not famous. So we don't have any design criteria. Not much of the design criteria is there, which comes out of torsion test. Okay. So unless you have a shaft in automobiles, there you need to check the torsion ability of the material. So you can do torsion, you can do tension, compression, tension, compression. But compression literature data is not too much. Okay. So you put the sample and then you can do, so for example tension or tension compression, you can do it in two ways. One is strain control and another is stress control. Okay. So if it is stress control, so then you have sigma max and sigma min defined, and then you will load the sample and it will reach. So in this case, the sigma max is higher than yield strength, monotonic yield strength. Okay. And then you will unload, and on the other side, it will go to the same value of yield. So sigma max, it will cross yielding and it will go there, and then it should come back. Okay. And then in the next cycle, what will happen if it is a strain hardening material, and it should strain harden. Not all the materials will strain harden. So based on cross slip also you can describe that which material will harden, which material will not harden much. So if it is cyclically hardening material, then for the same amount of stress, it will achieve lesser amount of strain. Okay. So this peak will be achieved earlier, and then it will go down back, and again that thing will happen. And in this case, the cycle will be shrinking initially, but after some time this thing will saturate. Okay. And the curve will not look like this. The curve will look something like this, and so on. Okay. And after few cycles it will saturate, so all the curves will be falling over and over on each other, so you will not see much difference. Okay. So in order to get the cyclic stress strain curve, what is happening is that stress is increasing. In this case our stress is fixed. It is not going beyond sigma max. So how do we get that curve? So there are two approaches. One is multi-specimen technique and another is single specimen technique. Multi-specimen technique is that you load different samples of the same material, and then you let them saturate. So your sigma, delta sigma is fixed if it is stress controlled. Okay, so amplitude of stress is sigma A is delta sigma by 2. Okay, so amplitude is fixed in this case. So let us say my amplitude is 500 megapascal, and I do this test and I let it saturate. So let us say it takes 1000 number of cycles. Then I take another sample of the same material and I do the testing at higher delta sigma. So 550, 560, 600, 650, 700 and so on. And I let all those specimens saturate, and then I plot the saturated curve on a single plot. Okay? And then that curve will look like this. And all these curves are coming from different tests, and all of those are saturated at different delta sigma. You can also do this by changing sigma mean. Okay? And then you join these points, and that is your cyclic stress strain curve. This is your cyclic stress strain curve, this one. Okay? So I told you that we can do it also by single specimen. So now tell me, how do we do it by single specimen?
Sir, after saturation, we can increase the stress.
Yes, exactly. So you take one sample and fix the sigma max, sigma min, let it saturate, then change sigma min, sigma max on the same sample, let it saturate, and so on. And from the same sample, from one single sample, you can generate a cyclic stress strain response. You can generate it also by strain control test, also by stress control test, and both of them have shown similar behavior in the range of the statistical scatter. Also, single specimen and multi-specimen techniques have given the same results under the tolerable statistical scatter. Okay? So, as I said, you can have cyclic softening, you can have cyclic hardening, you can have some material which shows softening and then hardening. Okay, so all those possibilities are there. But these softening hardening will saturate after some time. And after that, the curve will be not changing much. Okay? And this saturation takes very few number of cycle in comparison to the total number of cycle which you need for failure. Okay? So in comparison to 10 to the power 6, 10 to the power 8 number of cycles, this might take only 10 to the power 4 or 10 to the power 3 number of cycles for saturation. Okay? And not only this, although mechanical response is important, and we see this behavior in mechanical response, but it is also found that other property of the material also changes. So for example, for different amount of strain, so if you apply strain controlled testing on a steel sample, and then you load it for different number of cycles, okay, and then you plot the value of resistivity, then it shows that the resistivity of the material changes as you increase the number of cycles of loading. This also saturates after some time in metallic materials. But in some materials, when you cyclically load, then you can have what is known as centrosymmetry, which is broken. And because of that, you can have some electric signal generation. So when you apply cyclic loading on a material, it can cause the material to generate some electric signal. This is not seen in metallic materials so far, but some people have reported this phenomena also in a few grades of steels. Okay, so a lot of properties which will change with cyclic loading. One of them is the stress behavior. So material's ability to respond to the external forces, and that is what we are interested in right now. Okay, so why it is important to do single specimen testing in this case? So another example is that a research was done where the SN diagram for the same material, for same set of data. So each set of data included 10 tests. So you have set 1, 2, 3 and 4 and so on. And it was ensured that the samples were made as homogeneous and similar as possible by manufacturing them from the same material, from the same rod. And for each data, the statistical importance was, that performance calculation was done, that the data is statistically significant. And after that, you plot the SN diagram, and that SN diagram for each set showed a difference. Okay. So the problem is that if I take two sets of data together, I'll get a different SN diagram, and with different combinations of the same material, I'll get different SN diagram. And based on that, my endurance limit will be different from each SN diagram, and my component might fail. So this happens because in every material you have different distribution of inclusions and secondary phase particles, and on those inclusions and secondary phase particles, the persistent slip band will lead to the formation of microcrack. So every specimen has its own fatigue life.
Can we consider Weevil distribution in that case?
That's what we do. Okay. So then this becomes a problem. So Weevil distribution was also used in ductile to brittle transition. Okay, and that paper we have discussed from Weevil, and Weevil distribution is also used in fatigue for finding out the probability of fatigue failure. So this becomes a problem of statistics, and there is huge amount of scatter. If you do fatigue test, you will not get any conclusive result unless you do a strong statistical analysis of the data. Okay. So same material condition can lead you to a probability of 20% also and 90% also. Okay. But then you have to see that for certain amount of amplitude or mean stress or strain, whatever you are applying, from Weevil analysis, what is the probability of failure. So you can define your tolerance bounds. If the probability of failure is less than 5%, then you should be doing it. So you can also decide how much probability you can tolerate. Okay. So after we have our cyclic stress strain curve and statistical distribution, then let us look at the SN diagram once again. So we have delta sigma and we have N, and you can also have delta epsilon and N. Okay, and you will have low cycle fatigue region and you will have high cycle fatigue region, and beyond that you will have some other region. So this is how the SN diagram looks like, right? So in the low cycle fatigue, usually, I can also say always, the stresses or strain situation are always higher than yield strength in low cycle fatigue. Okay? And so there, the fatigue behavior is described by the amplitude of plastic strain. Okay? So because that is significantly higher. So in this case, this is my epsilon elastic, and this much amount is my epsilon plastic. So this becomes higher than the elastic strength. Usually elastic strengths are very small. Okay, so because your Young's modulus for metals are very high, so in that case this can be related to the fracture, monotonic fracture strain, and then number of cycles to the power something.
So
Okay, this is an empirical equation. There is no theory associated with it. This also can happen if instead of stress you are fluctuating temperature. So then you will have thermal strains without any force. If you are just fluctuating temperature, then also you will have fatigue failure. Okay, you can have a combination of these also. If the temperatures are higher, obviously, only then you will have thermal strain. And when temperatures are higher, so for example, your sample is going to, let us say, 600 degrees Celsius for 10 seconds, and then it is dropping to room temperature, and then it is going back to 600 and so on. So you obviously have thermal strain because of thermal coefficient of expansion, right? Apart from that, for this 10 seconds, you also have creep deformation happening, right? And you also are having fatigue with it. What else is happening? With increase in temperature, your yield strength is decreasing. So amount of plastic strain is variable. It is not constant because your yield strength is changing with temperature. Okay. So if this happens, then your material is going through a lot of stresses at home, at workplace, everywhere. Okay. So, and then if something is missing, then you put some sulfide, nitride, some acidic environment, and then just kill it. Okay. So this is in low cycle fatigue, and in high cycle fatigue, what will we have? In high cycle fatigue, instead of strain, we should have a relation with stress. Okay, so I can write the amplitude, which is delta sigma by 2, will be equal to failure stress, which is when, and there I have used B, so here I will use C, because A I am using for amplitude. So similar equation, right? And so this equation is valid here, right? And that equation is valid here. So how can I define the total curve, the full curve? How can I define that? What should be the equation for the full curve? And what will be the location of transition from LCF to HCF? What will be the equation for full curve? Rudraksh,
The sum of
आ जाओ.
so for full color equation will be the sum of two and for a limit.
You just do it. Just tell me what is it. Integration.
No, sir, limit.
Okay. Limit.
Limit जो इनका intersection point होगा
रखो. Full expression दो मेरे को. करो. कॉपी में करो. सौरभ.
Sir, intersection point n dash मान लेते हैं.
Okay. Zero is less than n dash. ये तो known चीज है, theoretically. दिलजीत आ जाओ. कुछ कर पाओगे कि नहीं?
नहीं.
ठीक है. So Rudraksh, you have added strain and stress together.
So इसको convert भी
So
करना
conversion is
पड़ेगा.
which
you can't do. Okay. So the total strain, or let us say delta epsilon, I can write as delta epsilon elastic and delta epsilon plastic. Now it's a piece of cake, right? Because that is coming from LCF and this is coming from HCF. Right? So from LCF, what did we have? We had this. Right? And from HCF, we had sigma f into 2n to the power c, and then I should divide it by elastic modulus and this. Okay? And here I can write, so this was for epsilon plastic divided by 2, right?
Yes, sir.
This was for epsilon, so this will be 2 into that,
Yes, sir.
and this will be also 2 into that. So instead of those 2, I can just write epsilon elastic by 2. And this I can write as delta sigma by 2e. But this will not be true if I have a lot of plasticity. Okay? So what will be the intersection point when I have these two terms equal? Right? That will be my intersection point. So this must be equal to that. Okay? So from that, what can I calculate? So I will have sigma f dash into 2n to the power c divided by e must be equal to epsilon f dash 2n to the power b, right? So I will have 2n to the power b minus c equals sigma f divided by epsilon
E also. E नीचे होगा. So E नीचे है.
o. So this I am taking there, this I am taking here, right? And then I can write 2n, which is transition, is equal to 1 by b minus c. Right? Okay. So now let us look at what happens when fatigue progresses to fracture, how that thing will be happening. So a lot of time of the fatigue test is consumed in initiation of a crack. Okay, that is the significant amount of time is taken in initiation of crack, and that part is gone when you have manufacturing defects already in the material. That part will be suppressed. If you have a very good material where you don't have manufacturing defects at all, okay, you don't have, for instance, porosity and things like that. I'm not talking about inclusion and all. If you remove inclusions and if you remove precipitates and everything, then obviously fatigue life will increase, but your strength will go down. Not because of inclusion, but because of precipitates, the strength will go down. Okay? So precipitates are not avoidable, but as much cleaner you can make your material, that much impact you will have on the fatigue life. Apart from that, what else can affect fatigue life is the residual stress. If you can somehow create, and why we don't have a lot of literature in compression fatigue, or we also don't have fatigue crack data on compression. So that we'll discuss when we are going towards crack. Because if there is a crack which has initiated, that will not open up in compression. It will open up only when you have tension on it. Okay. So if you need a value of sigma which can open a crack, and then you are going to a sigma which is also closing this crack, so you are going in compression, that scenario is better for the life of the material in comparison to the scenario where you are not going to compression at all. Okay? And then if you have a stress field which is compressive in nature, and this value is, let us say, sigma m, then whatever stress you are applying in tension, the effective stress is sigma minus sigma m, because compressive stresses are opposing the effect of tension. So the net effect is lesser. So this is how residual stress will play a role. Okay? So on samples you can do some mechanical working so that there are compressive stresses already in the material when you make the component, and then you can increase their fatigue life. So you can increase fatigue life by making the material cleaner. So you shouldn't have segregation, you shouldn't have a lot of inclusions. So for example, if you have cast iron and if you have a spheroidal cast iron, then out of these two, the fatigue life of spheroidal grey cast iron is going to be larger. Also, monotonic strength will be good for this thing. Not strength, but ductility. Okay. Apart from that, you can introduce compressive residual stresses. How can we introduce compressive residual stresses? By compressing them. How can we do it? Do you know any process which can introduce residual stresses?
Sir, I think reaction with sulfur produces, sir.
Reaction with
on the
sulfur?
surface,
Yeah.
sir, produces residual compression. Sir, in case of steels.
If I react the surface of the steel with sulfur, then how the residual stresses will come?
Sir, sulfur replaces. Sir, you are not very sure.
Okay.
Sir,
Today is what? Tuesday. We have class tomorrow.
Yes.
तो कल बताओ मेरे को ये process. सबको बताओ.
yes, sir.
Sulfur वाला. Okay.
That's what I mean.
Is there another process?
Short peening.
Short peening as well. So what is short peening? Short blasting. What is it?
Small balls are scattered onto the sample.
How small? आप लोगों ने किसी ने देखा है शॉर्ट ब्लास्टिंग?
हाँ.
देखा है? आपने देखा है? नहीं देखा है? So he has explained the process. You have a lot of balls which are thrown, bombarded on the steel, and those will create indent. It's like a Brenell hardness thing, but in this case, ball is very small. Okay. So that impact will create a compressive residual stress, and your fatigue life will increase. Okay. So
सर तो सरफेस थोड़ी खराब है,
surface खराब हो सकता है,
फटीग लाइफ को डिक्रीज करें.
नहीं भी कर सकता.
Compression.
So that is optimization. सरफेस खराब होने का मतलब क्या है?
सरफेस फिनिश है.
Surface finish. So surface roughness, if you have crest and valleys on surface which are in this form, so you have sharp kind of thing, which is usually the case, right? And then if you mirror polish it and you do short peening with a ball diameter of something micron, then you will have a surface which will be like this. Okay, so in comparison to that, this is still better. And then you have a residual stress here, which will not allow. And how surface is going to affect the fatigue life, that we will see. So this is just the cell structure formation. Okay, for wavy and planar dislocation cell structure in copper wire. This was by torsion, right? Okay, and well, this is another example. So persistent slip band, and this is the example of intrusion and extrusion on surface of a nickel specimen. So what is intrusion and extrusion, that also we'll see. This is what intrusion and extrusion is. Okay. So in each cycle, what is happening is that you have some deformation going in this direction, then a few of them are going back. This can happen at the interfaces. It can happen at the interface of an inclusion. It can happen at the interface of the grain boundary. It can obviously happen at the surface. Okay, and so now look at the probability where it can happen. So number of inclusions are limited, right? Number of boundaries are limited, but the surface is too high. So a lot of intrusion and extrusion can appear on the surface of the material, and this is why surface is important. Okay, if you already have a rough surface, then formation of intrusion and extrusion becomes very easier, because you don't need that many number of cycles so that it starts acting as a surface crack. This is a surface crack, very small in dimension, but it is a crack on the surface. If you already have intrusion extrusion, then you need very few number of cycles to make it critical, so that you have, so then it will be again in the loop, because you will have this intrusion which will raise the stress because it's a crack tip, so you have higher stress field that will cause more deformation there, that will cause more damage there, and then you will have a short crack appearing. So intrusion extrusion you can see at the surface of this inclusion, okay, and because of which a micro crack has generated. So so here again you see the mechanism. So persistent slip bands are forming at the boundary, and then they are creating extrusion and intrusion, and so okay, so that is happening here in inclusion, because inclusion will not deform in that way. Inclusions are usually very brittle, so they will not have, in comparison to metal, they will not have any fatigue life, none. They will break maybe in the first half cycle. Okay, so this initiation of a micro crack takes a lot of time. For a good surface smooth sample, it takes the significant amount of time in formation of this crack, and this crack is, in comparison to whatever cracks we have studied, it will not behave like that, because these cracks are very, very small. So then we come to the definition of what is a crack. When do we call it a crack? When do we call it a short crack? When do we call it a void? When do we call something a vacancy? Is vacancy a crack? No. Is void a crack? Yes. It's a blunt crack. But we cannot call it crack, because the dimensions of this thing are very, very small. They are smaller than these cracks which we are talking about. And these cracks will also not follow that easy the fracture mechanics which we have studied. Okay, so they are of the size of grain size and sometimes smaller than grain size. So they are heavily influenced by the surrounding slip bands. They are also influenced by the grain boundaries, and they are also influenced by the properties mismatch of a precipitate which is there. Okay, so ignoring all those is not possible there. And then think about the dimensions which we had of an ellipse in our fracture mechanics calculation. Okay, so their major and minor radii are of very small dimension. So short crack in fatigue is itself a different case of study. So anyway, so we'll discuss this thing in the next class. So you can just see this picture where stage 1 crack growth, which is the initiation of a micro crack, develops. So this is a real picture, and you see the crack is not propagating like you expect to propagate in fracture mechanics. Okay, so it is following the slip bands. Okay, and you have primary slip bands there, and the crack will join it. You have a lot of slip bands formation, intrusion, extrusion on the surface. So the crack will initiate from there. And the other important point is that if your stress levels are very, very small, very, very small, so that you are below endurance limit, in that case also these things are happening. But what is happening is that whatever is forming at the surface is not enough to cause a crack, but they are getting accumulated inside. The damage, the PSBs, are causing intrusion and extrusion on the grain boundaries inside the material, at the barriers, at the inclusions inside the material, and for a very long time it may happen, and it does happen, that a micro crack forms from inside and not from the surface. For low cycle, high cycle fatigue, it is 99% the truth is that the crack appears from the surface. Okay, but when you go to very high cycle fatigue region, then the crack starts from subsurface. So you should not interpret it in this way that you can have a bad surface of the sample. Then it will start from the surface. So for the same surface condition, if you are in high cycle fatigue, the crack will develop at the surface. If you are in very high cycle fatigue, the crack will develop subsurface. Okay. Right, how much time do we have? We have 4 minutes. Okay, so I can discuss one more thing. So for different values of mean stress, if I change the value of mean stress, I will have different allowable value of amplitudes, isn't it? If I change the value of mean stress, so if my stress cycle is this, I am going to 500 and minus 500 and my mean is 0. Okay, then if I choose my mean to be here, I can go to a different level of amplitude if I want to have the failure in same number of cycles. Right? So allowable amplitude will change. So if I increase my amplitude, how much higher amplitude can I have? How high of an amplitude can I have for fatigue test?
2 times.
Yes, maximum strength. So ultimate tensile strength. Right? So if I plot sigma amplitude and number of cycles for failure, then if I start here, I will start at ultimate tensile strength, and as my mean stress decreases, then I will be increasing the allowable amplitude which I can have, right? Or allowable. So if this is my mean stress, then I can increase the amplitude. So here I cannot have any amplitude. If I go lower than yield strength, I will have a higher amplitude. If I go even lower, I can have more amplitude, right? So this data goes to, well, I have plotted it wrong, so I should plot it in this way, so that when sigma mean becomes negative, then I am going in compression. The diagram is also okay, right? And in compression, we don't have much data. We have data only here. Okay, so this is sigma mean line, and this is your delta sigma. So this is delta sigma by 2. That's the amplitude which can increase. Okay, and in compression it is just extrapolation. It may not be true, because in compression it cannot be just extrapolation, but there is no data, not much data. Okay, so this kind of representation of allowable amplitude with varying mean stress was given by Goodman, because he was a good man. It is called Goodman's diagram. I'm not writing diagram. Okay, so read about it, Goodman diagram, and also try to plot it. I mean, practice plotting it. That's it.